And now we have Susan talking about star formation history of Quiescent Galaxies.
So thank you. Now for something almost completely different. I'll be talking about observations of star formation histories of quiescent galaxies. This is work I did with my former postdoc, Camilla Pacifici, and members of the CANDLES team, including some of the people in attendance that are listed here. So I give a lot of talks to committees being at the Institute, so I'm going to walk you through, hopefully hold your hand as mostly simulators through some of these observations. So hold on. So this is starting from basics. This is the Hubble tuning fork diagram. While it is now used as a morphological diagram, it was first presented as an evolutionary sequence. So in this diagram, Hubble postulates that quiescent galaxies turn into star-forming galaxies. And we now know that this is not the case. It actually goes in the other direction, in that you have star-forming galaxies that turn into quiescent galaxies. So this talk will focus on, I'll show you, there are some pretty pictures. For those of you who know this already, you can just fade out and look at the beautiful images, but we're going to talk about how quiescent spheroidals form. This is a spheroidal galaxy in the local universe, and it is quiescent. So the classical picture that dominated for decades, what do I hit, seminar, lecture? Yeah, I do. I'm going to turn them on and off, sorry. The classical picture that dominated for decades of how spheroids formed was that they formed in a single burst in the early universe. Breakthrough came about 10 years ago with luminosity functions led right here by Sandy Faber and the Deep 2 team. We found that quiescent galaxies increased in numbers by a factor of 2 to 4 over the last 8 billion years since a redshift of 1. So they couldn't have formed in a single burst early on in the universe because they had to continue to form. This is a real breakthrough. And Sandy found, and as did others, found that quiescent spheroids must form from star-forming disks. And this, as many of you know, kicked off a whole subfield. So star-forming galaxies continuously add to the quiescent population, but it is unclear how still to this day. So again, we're turning beautiful disks like this into things like this. This is a cartoon following some of Sandy's work, where we have, this is really a sketch of galaxy populations. We have red galaxies and blue galaxies, color and mass. Galaxies, as you plot them as individual points here, pretty much follow two clouds, as you will know. It's unclear how one galaxy from the blue star-forming area must move into the red quiescent area. So we're going to investigate this with measurements of the star formation histories of quiescent galaxies. How do we measure the star formation histories? Well, first we get a sample of quiescent galaxies, and I'll explain that in a bit. We get 850 galaxies from the CANDLE survey, and then we fit their spectral energy distributions. So this is an example spectral energy distribution. The data are in blue here, and the model is this black solid line. The SEDs we measure are what we call broadband SEDs, or we measure the galaxy in different wave bands. This is U-band, Hubble, and then IRAC channel 1 for this guy here. This is magnitude versus wavelength. And so we fit this with our models. We have a whole library of galaxy models, and I'll explain that to you in a bit. And they vary in terms of star formation history, metallicity, stellar mass, age, as you all know. The model star formation histories that we particularly use are physically motivated. I'll explain that in a bit. And then we determine the best estimate star formation history for each galaxy in a Bayesian sense by averaging all of the models weighted by their likelihoods. Okay, so we know galaxies form hierarchically, and much of your field has told us this. This is from Wiesa Wechsler's thesis. It's a dark matter halo merger tree. It shows us that a dark matter halo here today, which should host a galaxy, is the product of many, many, many little galaxies that were once individuals that then combined to form this galaxy. It is formed hierarchically. And then these are star formation histories of local galaxies. This is the LMC, the SMC, stuff you know from the night sky. They're measured star by Dan Weiss here. This is star formation rate as a function of time, and you can see it's stochastic. You can't really fit a functional form to this and have a good fit happen. It's not a declining tau, it's not a tau, it's somewhat constant, but it does go up and down, stochastic. So this motivated Cami in her thesis, Camilla Pacifici, to not adopt a typical tau or a typical functional form for a star formation history, but to actually adopt star formation histories from you guys, from numerical simulations. And as I think Vadim showed us, or some people showed us throughout the talk, throughout this conference, star formation histories of simulated galaxies are rather stochastic. Cami in particularly used star formation histories from a semi-analytic post-treatment of the Millennium simulations from De Lucia and Blaiseau, 07, but she's done it with Hydra simulations, and we found very similar, if not the same results. Another important thing to mention about the way we did this is that most chemical enrichment histories in our models increase with time. And we also adopt chemical enrichment histories from the simulations. They're always increasing. This is an important prior. It's typically assumed in this business that metallicity does not evolve, which we know is not the case. So we're going in with priors, saying the universe is hierarchical, must have a star formation history that is rather stochastic, and then also that the metallicity history is increasing with the enrichment history is increasing with time. So this is how we estimate the star formation history, the best estimate star formation history for a given galaxy. What's plotted here is star formation rate versus look-back time, and these individual lines are all different star formation histories. In gray here are individual 25 best fit models for the galaxy. We have 500,000 models. These are the best fitting 25 for this one galaxy. And then what we do at every point in time is we take, we basically take the average, we take the average over the star formation histories weighted by their likelihoods. And that's where we get out this solid line in here. Okay, so this is an average over all these, over all these star formation histories over time. The 25 best ones are shown on here. The dotted line is the interquartile range, or the 25 to 75% fit here. So we do this for individual galaxies. We do this for 850 of them. That's right. And then we're going to now do the Santa Cruz plot soon, and we're going to bin them in mass and in redshift. Okay? So this is one of those bins. This is a bin at redshift 0.3 of 10 to the 11 solar masses, 24 galaxies. Star formation rate versus look-back time again. This is today. This is the past. Because this is redshift 0.3, this is today. This is actually redshift 0.3 here. We don't know what happens. Whereas we can infer what happens here. So individual galaxies here are plotted these light dotted lines in here. So they're calculated like in the previous slide. We've only showed a few on here, otherwise it would look quite messy. So we're now showing the median star formation history for this stellar mass in redshift bin. Here is a solid line, and the interquartile range now is shown in red. Okay, so this is the average star formation history for galaxies at redshift 0.3 and stellar mass about 11. Now I'm going to show you one of the giant Santa Cruz plots that we love to plot here. I'll walk you through it in the next. We've analyzed this in many ways. Here's star formation rate versus look-back time. That's the axes in each panel. This is redshift 0.3, and it increases in redshift as you go over here. Stellar mass is color-coded for ease of consumption. It's stellar mass of 9, and you get heavier, you get red and darker, right? Okay. You first look at this, so don't forget the gray is what we don't observe. So this is redshift 0.3. We just don't know what's going on between here and here, and that gray area gets larger as you go to higher and higher redshifts. So what you see here, very, very interestingly, and not super surprisingly, is they go up and down at high redshift. They're very compressed star formation histories. Well, there's not much time to form a quiescent galaxy, so if they are quiescent, then they kind of have to do that, up and down rather fast. You also notice, I think the first thing you notice is they're all bell-shaped. They go up, they reach a peak, and they go down, and the size of the rise and the decline do change. So now I'm going, and then you also notice at lower redshift, they are a lot more extended. Okay, so now this is another somewhat complicated plot, but I'll walk you through it. We're now plotting the look-back time of the peak of those star formation histories versus the stellar mass. We're doing it in different bends. of redshift. Let's look at the first one. This is low redshift, 10 to the 9, so log of 10 to the 9 solar masses, and this is 10 to the 11. And what you see very nicely is that at lower redshift, the look-back time of the peak is a function of mass. Low-mass galaxies reach their peak later in their lifetimes, about 5 to 6 gigayears, than high-mass galaxies, which reach them about 8 to 9 gigayears. And then this trend with redshifts does seem to flatten out a bit. So, and then high-mass galaxies reach their peak earlier, and then high-mass galaxies form and quench fast. Another thing we can measure, amongst many others, is the decline of the star formation rate, of the star formation histories. This is also the lowest redshift bin, and then you go out in redshift. Each little one is its own little plot in stellar mass. So at low redshift, the declining phase in low mass galaxies is about 1 gigayears. It's actually fast, and then it's slower in higher mass galaxies. At high redshift, the universe is young, so the decline pretty much has to be rather rapid by construction. They go up and down rather fast. So this summarizes it rather qualitatively. So this is a plot of the star formation histories of galaxies, of kind of representative populations of galaxies. So at high mass, at high redshift, they do this up and down rather fast, on average. Locally, they could do that, but they're rare, and only about 10% do this locally. At high mass, so now at low redshift, the high mass galaxies, they go up rather fast, but they take forever to quench, on average. Individual ones can do differently. And low mass, low redshift, they go up rather slowly, and then they quench rather fast. And as many of you know in this room, and have been probably thinking just this can hint at some quenching mechanisms. So back to this plot, the cartoon plot. How do you move galaxies from here? They're star forming and they're disk-like to here, and they're spheroidal and not forming stars. At low redshift, so what are some hints from that? We get some hints from measuring these star formation histories. At low redshift, they quench rather fast. This could be a catastrophic event like stripping or strong feedback. It can be environmental. You might imagine them falling into an environment and losing their gas rather quickly. At low redshift, high mass galaxies, they take a while to quench, on average. Gas accretion is stopped, and then galaxies tend to use up their gas residually, their residual gas rather slowly. And then at high redshift, you're going to go up and down rather fast. It's quite dramatic. The time scales are about a gigayear, so it is consistent with halo quenching, though. It doesn't have to be incredibly dramatic with an AGN. And then I will just leave you with that simple story. Thank you.
Okay, we have time for questions.
I think so. Tammy and I have discussed that. Good idea.
Another question while the next speaker setups? Yes.
Mm-hmm. It's about the dynamical time at that point in time. Yeah. Okay, maybe it is longer, but approximately so. But I think your simulations should be able to reproduce this.
Another question? If not, let's thank. Yeah, you have one.
So one aspect of the mass dependence that has to be shown here, but that you didn't explicitly mention, is the basic downsizing story. Namely, the higher mass galaxies go through their whole process of star formation and quenching earlier, the lower mass galaxies later.
Yes.
Do you want to elaborate a little bit on that? Because, I mean, it was something I was expecting you to mention, but it didn't pop out.
That's what we find. I can bring up I can't really bring up plots right now, but I wanted to keep short and sweet, so it's not too much information. But yes, we're totally consistent with downsizing.
Okay, let's thank Susan again.